chapters he has published. He's delivered 126 plus invited lectures, and he has guided 18 doctoral theses and 95 MTech theses. He has filed a patent by Heat Pump Laboratory at IIT Mumbai. Indian patents 33, from which 18 is granted, 12 is defended, awaiting in grant, and 3 is awaiting in examination. He is a 3 European patent and 7 PCT. He has a technology transferred or product license or commercialized 27. He was a past president of Life and presently life member of ISHRE Mumbai chapter and member of ASHRE. Is a RL Regional Center and November 2020 until October 2021. He has received award from Nina Saxena for technology development and commercialization, Bry Air for product design, and Dr. P.K. Patwardhan technology development, Vasvik technology development, and Eureka business plan. We are very lucky to have your session, sir. You can please start your session, sir. Thank you very much.
Namaskar. Welcome to the session. So as you know, I will be talking on sustainable development based on energy efficient technologies. These are some of the technologies that we have developed at the Heat Pump Laboratory. So first we will briefly look at the need and scope for sustainable development. Okay, why do we need to look at sustainable development, and what are the possibilities, what are the options? So then we will look at some of the energy efficient technologies, a brief overview of some of the technologies first. In these, we will be looking at electric and heat driven multi-utility heat pumps, exhaust heat recovery systems, and renewable energy based systems. And in these, we will be seeing superheat recovery water heaters or process fluid heaters, heat pumps, multi-utility heat pumps, waste heat recovery, waste heat from industrial processes, industrial exhaust, or this exhaust from air conditioning systems, and so on and so forth. And in that, we will look at exhaust heat recovery units from engines, gensets, gas turbines, furnaces, stenters. And then we'll look at some plastic and aluminum air-to-air heat recovery units for air conditioning application also. We'll look at some of the applications of superheat recovery, water heaters and heat pumps in detail. We'll look at the salient features of these systems, which are based on tube-tube heat exchanger, one of our key patents, which offers several advantages. Then we will also look at some of the case studies, one for 60-ton chiller-based superheat recovery unit. Then another is a 270-ton ammonia-based refrigeration system superheat recovery unit for a dairy. Then superheat recovery for fast food restaurants like McDonald's and others. We have more than 340 installations in these itself. And then we'll look at heat pump, multi-utility heat pump installations in automotive factories and various other applications. The solar collectors and the salient features and their applications. We'll look at solar air heaters using plastic extrusions, as well as which go up to 100 degrees centigrade or so. And we have aluminum extrusion based systems which go up to 120 degrees. And then we have evacuated glass tube based collectors which go up to all the way up to 320 degrees centigrade. And these can be used for drying, industrial heating application. We'll see some of the case studies here in brief. Then we'll look at solar steam generators using EGT and with and without heat pipes. We also have solar steam generators, flat plate type with aluminum extrusions. Then we'll look at liquid desiccant based multi-utility heat pump. I think Professor Mehta might have shown you some of the things, and the subsequent students' work is also reported in ISHRE journal recently. We'll look at the evacuated glass tube based adsorption refrigeration system, which uses activated carbon ammonia as a working fluid, and then we'll conclude based on some of the things. So coming to the first, this need and scope for sustainable development. Sustainability with respect to environment and sustainability with respect to economics also. Okay, just environmental sustainability, if it is not economically sustainable, will not be adopted by the potential users, and then we will not benefit from the systems. So on the environmental sustainability side, first the first thing we need to do is reduce the utilities required. After reducing the heating and cooling requirements by judiciously selecting the operating conditions, we can judiciously select the integration of various components and so on and so forth, and then try and reduce the requirement for cooling. Then after reducing the requirement for cooling, then that requirement for cooling can be catered to using some of the best, most efficient systems. Okay, and then the systems which we are looking at should be also using working fluids which are environmental friendly. So if you are using refrigerants, they should either be non-ozone depleting or very low ozone depleting potential should be there. If the global warming potential should be also as low as possible. So first is, of course, if you reduce the heating and cooling requirement, then your system size reduces. So automatically your refrigerant size, required in the system will reduce. We will also see examples for reducing this by integrating multiple utilities and obtaining multiple utilities from a single system. Then we'll look at economic sustainability. In economic sustainability, basically we are looking at low life cycle cost. Now, life cycle cost can be reduced by reducing the initial cost and or reducing the operating cost. Ideally, if we can reduce both, that is going to give you the least life cycle cost. So if you look at energy conservation, we'll look at first reducing the demand for electricity, demand for utilities. And then we'll look at low life cycle cost this, and then we'll look at environment friendly. So in this, we can see that the multi-utility generators like cold utility, hot utility, the dehumidification utility, potable water generation as a utility, electricity as a utility. So if a single system can generate more than one. Now, when we talk about an air conditioner, it only generates, typically only generates cooling. When we talk about a heat pump water heater, it only generates hot water. If you look at a boiler, it only generates this. If you look at a DG set, it only generates electricity. So instead of doing that, can we have a DG set and recover the heat from the exhaust, and then that recovered heat can be used for dehumidification, or that recovered heat can be used for potable water generation, and so on and so forth. Similarly, can we have a heat pump which generates its primary utilities to generate cooling and dehumidification, but along with that cooling and dehumidification, can we also generate potable water using it? Can we also generate hot water using the same system? And so superheat recovery is one of the options which can not only improve the COP of the chilling system and increase its cooling capacity, it can thus lead to reduction in demand also. Okay. Now, solar can give you free hot water when the sun is shining, but it cannot reduce your cooling load, or your power consumed by the cooling system, subsystem, air conditioners, chillers, and so on and so forth. But if you do superheat recovery, you not only recover the hot water or hot utility as a bonus utility, okay, which is absolutely free of cost because your power consumption of the chiller is actually reducing, not increasing at all. Okay, so not only that you reduce the chiller or refrigeration system power consumption, you have actually also increased the utility that is generated from that. So we'll be looking at those options. Then preheating of boiler feed water can be considered as a free utility, and if cooling is the thing, or it can be looked at vice versa. Your boiler feed water is the primary utility and cooling is the bonus utility. Then peak demand for domestic water heating can be reduced by over 95%. If you see, if you're using electric water heaters and things like that, most of the electric water heaters might operate during the morning rush time or the evening time and things like that, depending upon the usage and the local culture. This. Now, all that instantaneous load because of the water heaters can peak up the total demand for the utility. And it might create some issues with respect to maintaining the voltage, current, and frequencies of this because of such spiked loads. So can we, the utilities will love to reduce the peak demands so that if the demand can be flattened out. So heat pumps can be one such option. And when you use heat pumps, you can generate and store hot water, and then the stored hot water can be used in very short time as and when it is required. So we'll see some of the systems of that type also. Of course, we'll look at some of the challenges in meeting multiple demands using a single system as we go along. So now we'll also look at low life cycle cost. How can life cycle cost be reduced? First is you reduce the demand and usage of use the efficient multi-utility systems to produce the utilities that are reduce the utilities that are required. So that is going to reduce your size of the equipment. So your initial cost can be reduced. Instead of multiple systems catering to multiple utilities being generated independently, a single system generating two utilities can be cheaper at times. Okay, so the total energy cost and the installed cost can also be reduced in this way. So your life cycle cost can go down. Co-producing utilities using a single system not only gives you lower initial and operating costs, it can also reduce the space requirement, and space also is at a cost in many of the situations. Okay, so if your space requirement reduces, you can use that space or rent that space for some other application, and so that also can reduce your life cycle cost. And generating multiple utilities using a single system can also reduce your maintenance requirement. In fact, by recovering superheat from this, you are reducing the condenser load, and by reducing the condenser load, your condensing pressure goes down, and by reducing the condensing pressure, the compressor operates at a more environment friendly environment, means reduced pressure ratio. It is less stressful for the compressor to operate under those conditions, and because of that, what happens is your maintenance requirement on the compressor, failure of the compressor also goes down. Now, good application engineering is, however, necessary to ensure that the integration of the multi-utilities being generated using a single system still meet the all the desired requirements of the user with respect to when they want the hot utility, when they want the cold utility, at what rate they want the hot utility or the cold utility is delivered, and so on and so forth. And of course, the primary objective of any designer should be to ensure that the reliability is maintained very high. Okay, so the user satisfaction is derived out of that. Now we'll look at environmental friendliness of these. Now, co-producing multiple utilities not only helps with respect to reduce space, cost, and other things, it also helps improve the equipment performance. So low energy consumption. Low energy consumption means low fuel input or electrical input. That means low emissions. Then since the cooling capacity and this also goes up, then your size of the system, compressor size and heat exchangers and other this can also be optimized and reduced, and that can help you reduce the refrigerant charge. So reduce refrigerant charge, and if the refrigerant is not very environment friendly, then again reducing the refrigerant charge helps in meeting the environmental concerns also. Reducing material usage. If multiple systems are multiple utilities are being catered to using a single system, then your usage of material to build the systems is also going to reduce, and so the embodied energy, that is the energy required to develop and deploy those systems which are giving you the required utilities, can also be brought down. Now, thermal pollution and CO2 emissions get reduced by using multi-utility generators. And then after we have catered to the reduced utility, after first doing internal integration of heat sources at low temperature and other utility requirements at low temperature by recovering heat judiciously, then the next option is to try and integrate systems, multi-utility systems, to reduce your peak demand for electricity or heat or energy or whatever it is. And after that only you should start looking at the renewable resource, because most of the time renewable resources are costly per unit utility delivered. Okay, because it comes in a diffuse manner, and also they are not available 24/7 most of the time. Okay, if you're talking about run of the river this, then maybe the river might be flowing this. If the river flows 12 months a year, then you might have that renewable resource throughout the year and throughout the day and night. But most of the solar or wind, other resources will have to be are not available throughout, and many times you need storage, and sometimes you need backup in spite of having storage, because if you have 2-3 days of non-solar this because of cloudy weather or something like that, then what do you do? So you need to have backups. So backups become essential for renewable, and they end up increasing the initial cost and this. So renewables, in my opinion, should be considered at the end after you have done judicious reduction of utility is required by selecting the operating conditions and other things judiciously, then integrating the systems judiciously to recover heat from various other sources wherever it is possible, heat or cooling effect, using waste heat recovery systems and so on and so forth. And after that is done, then deploy multi-utility generators to minimize the demand and minimize the emissions because of that, and minimize the working fluids required in the heat pumps and other systems to reduce the environment impact. And only in the end, we should go for renewable based systems, which of course eliminate the need for fuel as and when the renewable resource is available. Okay, they will need heat pump as backup. Water heaters are based on this. Now coming to some of the systems that we have developed at the heat pump lab. You can stop me if anybody has a question. Either maybe I can take a brief stop here and ask questions if anybody has any questions at this point in time. No questions? Are you able to hear me? Hello?
Yes, sir. Yes, sir.
Oh, okay, there are no questions. Okay, so if there are no questions, I will proceed with the rest of my presentation. So we'll first look at the multi-utility heat pumps and superheat recovery water heaters. Now, this slide shows some photographs of the multi-utility heat pumps and superheat recovery unit. The key technology behind this is the tube-tube heat exchanger. As you can see, one of the simplest configurations of the tube-tube heat exchanger is displayed here. So you have two tubes put up side by side. So one of the tubes is carrying the hot fluid, and the other tube is carrying the cooler fluid, which needs to be heated. And then they are thermally bonded between the two tubes. So in case any leakage is there from any of the fluids, it will go into the atmosphere and not go into the second fluid. So that is the primary advantage of this. And because of this advantage, what happens is you can directly heat or cool the process fluid or potable water, which otherwise may be a concern, because in case the refrigerant leaks and mixes with the water which you are heating up, that water may not be considered, may not qualify as potable water. Okay, it may not be consumed or things like that. Okay, so this judicious integration of this configuration into various technologies that we have developed helps us directly interact with the process fluids in the plant, whether it is a dairy or a chemical factory or a industrial environment like automotive industries and things like that. We can directly heat and cool the fluids. So that eliminates internal extra loops of the heat transfer media and extra pumps and controls for those and all those things, and helps improve the COP of the overall installation, because the lift of the heat pump can now be reduced, because we don't have to heat up water and then that water is to heat up the process fluid. We can directly heat the process fluid. So one LMTD is reduced, one LMTD is eliminated, and so our heat pump COP also improves. Now this is an industrial heat pump. As you can see here, this is a all stainless steel body heat pump which was developed and deployed in Mahindra and Mahindra in the automotive industry, where it was primarily used to produce hot water. Heating solution was heated from 50 to 55 degrees centigrade, and that hot solution was then used for cooling, dehumidification, for washing of engine components. Okay, in the assembly line. So earlier they were using electric heaters. So compared to electric heaters, if the COP of the heat pump is 3, then we were saving 66% energy. If the COP of this was going to up to 4 also in some this circumstances, then we are saving 75% of the energy that the client was earlier using. And not only that, in addition to that, we were giving free cooling, because the unit was kept in the plant room and it would suck air, it would filter it, cool it, dehumidify it, recover the heat from that, and then that heat was delivered in the condenser of the heat pump after the compressor had done some work on it. So we had to supply the compressor work, and then the condenser heat would be tapped out for this using the tube-tube heat exchangers. So some of these heat pumps have been operating for over 8 to 10 years now in some of the locations, and they have proven their reliability. The tube-tube heat exchangers have proven their reliability. We'll see some examples where at Hotel Fariaz in Kolaba, it operated for 11 years without a single service call. Okay. Then this is the first de-superheater which we developed for McDonald's for this 3.8 kilowatt cooling system, the kitchen AC. And we were recovering hot water, and that hot water was used for this. Another installation which you see here is also a multi-utility heat pump. So this was a DX system for 24 tons. The 2 compressors of 12 ton were housed inside this outdoor unit. This was generating free hot water for sanitation, as well as it was generating potable chilled water. And this potable chilled water was then used for dispensing as Coke or chilled water for drinking and other beverages. Okay, so instead of cooling the carbonated water from 30 degrees, 32 degrees, all the way down to 7 degrees in the tabletop, countertop Coke dispensing unit, okay, beverage dispensing unit. In this case, the water was pre-cooled from 32 degrees to 15 degrees or 12 degrees. And then that 15 or 12 degree water was further cooled down to 7 degrees in the countertop unit. Now this reduced the cooling required at the countertop unit, and it increased the amount of liquid or the beverages that a single unit can discharge. It increased almost 2 to 3 times the capacity of that countertop unit. So the cost of the heat exchanger to recover the cooling in this particular case, the additional cost of the heat exchanger to recover the cooling from this case was much, much lower than the cost of the eliminated beverage coolers because of the increased capacity. Also, the excess heat after recovering hot water was dispensed using evaporative condensation. Now, because of evaporative condensation is on one side you would have water evaporating, and the other side you will have the refrigerant condensing. Now, we will see what type of equipment, what type of patented equipment we had deployed there in a short while. That was rotating contacting device, diabetic contacting device. Now, using those diabetic contacting device, we were able to reduce the condensing temperature significantly, and that reduced condensing temperature led to reduced power consumption because of reduced condenser pressure, reduced pressure ratio across the compressor, led to reduced power consumption of the compressor. Not only that, hello. Yeah. Not only that, we were also able to reduce the noise of this system significantly, because a conventional 24-ton air-cooled system would have much larger fans, and the total power consumption of the fans compared to air-cooled system in our system, the power consumption reduced by 9 times. And that was partly because much lower power airflow was required, and our pressure drop through our contacting device was less than 1 mm of water column. Okay, that is just 10 pascal as compared to around 100 to 150 pascal through most of the air-cooled condensers. Okay, so then the other thing about the multi-utility heat pumps was also our tube-tube heat exchangers enabled us to reduce the inventory or the charge of the refrigerant significantly. And in fact, Professor Matawala, who had worked at that time on this project, from LD, So the power consumption, the unit was capable of generating cooling effect from 12 to 7 degrees. Water was being chilled from 3 to 3 with a COP of 3 to 3.3, and simultaneous heating was possible with 3.9 to 4.2 COP, while water was heated in a single pass from 25 degrees to 55 degrees centigrade. And this was possible with a very low charge of refrigerant, that is just 0.1 kg per ton. Now we are going to integrate some systems where even the latest systems, even larger ammonia systems, it is quite challenging to get down their charge to less than 0.1 kg per ton, which we had achieved more than 10 years ago. Okay. So reducing the charge in the system is very useful, as I said, because that is also it reduces the hazards if the working fluid is, if the refrigerant is toxic or flammable, like in the case of ammonia, and in case it is using a refrigerant which is not ozone depleting and not having zero ozone depleting potential and zero global warming potential, okay, then in that case reducing the charge also makes the system more sustainable. And of course, generating two utilities from the same thing. Now, you don't need a separate heat pump to generate the hot water, and you don't need a separate chiller to produce this. So a single system producing both of them would certainly reduce the charge, because the charge in the two systems is going to be much more than charge in a single system, and so on and so forth. And plus, of course, the energy consumed is less. So your CO2 emissions are reduced because of that also. Now, here is a situation where we have deployed the system at NTPC in Netra, their R&D headquarters, way back in May 2017, and I believe it is still operational, and they're quite happy with it. And this system is a 6-in-1 heat pump. So it generates 6 utilities using a single system. Now, one would wonder what the utilities are. So let me first take you through the utilities. The first utility is dehumidification of fresh air to maintain the indoors, cooling and dehumidification of fresh air to maintain the indoors at 27 degrees and 60% RH. Note that the temperatures are selected in such a way that they are not increasing the cooling dehumidification utility significantly. Okay. And yet it is comfortable enough. At these conditions. So for summer and monsoon condition, we would supply air to maintain the indoors at 27 and 60. So the actual air supplied will be lower than this. So typically 21 degrees, 22 degree air will be supplied into the zone. And then the second utility is the hot air that was supplied, that is supplied in winter. So in Greater Noida area, where this institute is, where this facility is located, in winter the temperatures go low, and so they need heating, and this also caters to heating. We supply 41 degree hot air for that using the same 12-ton compressor-based system. So these are the two primary utilities, and the heat pump is operated based on the requirement of the your canteen. So this is serving the canteen, their main canteen in the whole building. And you can see this is almost 1/3 the area which is seen here. The other half is on this side, and then there is some more on the front side. So this is the actual area is almost 3 times this. And this unit is sitting right outside this wall on this side, and then the air is being communicated inside, and we have made the ducts and all those things. We are ourselves members of the heat pump lab, went and integrated these. I was also present at that time. This entire heat pump and all these earlier systems also were fabricated in the lab itself by our team. Of course, some of the components were for cutting, bending, and all those things. We'll send it out, but most of the welding and refrigeration system integration and all happened within our facility by our team. So in this, the other utilities was the potable water chiller for 150 liters per day at 15 to 18 degrees for drinking purpose. So anytime during the day, you can open the taps wherever they are located and and then you can get chilled water for drinking. So this was filtered water, which was filtered RO water, which was supplied into the unit, and then the unit would cool it from whatever be the temperature, 30, 32, or even 37 degrees centigrade down to 15 or 18 degrees centigrade, and that can be used for drinking. Now, the heat pump operated only 6 to 7 hours a day, typically. Okay, 2 hours during the morning breakfast period, 3 hours during the lunch period, and 1.5 during the evening tiffin period. But the hot utility, the chilled utility, okay, is available 24/7, not just on the days on which the institute is working, but even on weekends, there was enough storage to allow water to be supplied to the watchmen and the cleaning staff and the gardeners and all those things who worked on the weekend also. And the other utilities that this system was producing was 2,000 liters of water being heated from 20 degrees to 60 degrees in a single pass, and then 200 liters of water at 95 degrees centigrade. So from 20 degrees to 95 degrees in a single pass without any pumps. All these utilities are discharged without any pump, neither during the storage phase nor during the discharge phase. Okay, so the heat exchangers are novel in that sense, and they were deployed in such a way that you could use these in that way. Okay, and then so you have these were two more hot utilities here in addition to the air heating, and then the sixth utility was a 1,000-liter refrigerated cabinet maintained at 10 to 15 degrees centigrade to preserve fresh fruits, vegetables, milk, etc. And the total cost estimated at that time, the operating cost saving at that time was estimated to be 2.85 lakh rupees, assuming 300 days of operation. And the first unit, the subsequent units could be this at 12 to 15 lakh per piece. And if it mass produced, maybe the cost can come down significantly, maybe even to about 8 to 10 lakh rupees or so. Okay, the payback period for this particular unit was around 2 years for a non-solar option. So if the solar collectors are not already deployed for water heating and hot water was not freely available using solar except for monsoon and other seasons, then the payback would be 2 years. And if the solar option is not implemented and electrical or gas-based this was used, then the payback was only it was less than 1 year payback. Okay. Then the other things that I would like to talk about is the air-to-air heat recovery. These were the units where we use plastic air-to-air heat exchangers to cool air from 42.9 degrees centigrade and 26.6% RH down to 25.8 degrees centigrade. Okay, the humidity, of course, is maintained, and so the RH goes up when the temperature is reduced. And this was possible using the exhaust air from the conditioned space. So when you supply the fresh air, the same amount of fresh air which goes into the room is going to displace same amount of stale air from the room, and that air from the room is going to be at the indoor condition. In this case, the indoor condition was about 26.6 degrees centigrade and 58% RH. Now, one would wonder how I am able to reduce the temperature below this in this heat exchanger. There is no violation of any law. We are just humidifying this air, and after humidification, the RH goes up to 90%. The temperature drops to 22.2 degrees centigrade, and this 22.2 degrees centigrade air is then able to cool the air from 42.9 degrees centigrade to 25.8 degrees centigrade in just a 2 feet long plastic heat exchanger. Okay. And of course, if you go through the details, you'll see that the blower power was very small. Okay. And it can be further reduced, of course. The pressure drops are much lower than the conventional heat exchangers of this type. Typical conventional heat exchangers, the pressure drops are of the order of 150 to 200, 250 Pascal. In our case, it was less than 50 Pascal. Okay. Less than 60 Pascal. Okay, then we would move on to exhaust heat recovery. Now, there might be gas turbines installed in a facility, or there might be gensets installed in the particular facility, and there might be exhaust heat available. So we can generate various utilities from the exhaust heat. We can heat up air for process heat, process applications. We can heat up water. Water can be heated in a pressurized state above at 100 degrees centigrade also. We have heated here thermic fluid right up to 250 degrees centigrade also. And we have generated steam up to 16 bars. And ammonia water solution can be regenerated, or liquid desiccants can be, streams can be regenerated using the waste heat from gensets and all those things. Now, there was a period when this was, by the way, the matrix heat recovery was my first patent when I came back to India from US in 93. Before I joined IIT in 94, I developed this technology during that 1 year, gotten the patent, applied for the patent, and licensed the technology before I joined IIT. Of course, we relicensed this technology to another client with this, and who had installed more than 60 installations in the industrial, this mainly in the industrial this, from right from 135 kVA DG set to 6 megawatt DG sets. And in fact, in one of the sites, there were 3 6 megawatt DG sets sitting right next to each other, producing the hot utility from that. This. Now, the beauty of this is normally steam generators from diesel engine exhaust are larger than the DG sets. Our systems were the size of the muffler of the DG set. So not larger than the DG set, but much, much, much smaller than the DG set. In fact, the size of the muffler, you can very well imagine what might be the size of the DG set. Okay, and our heat exchanger is insulated heat exchanger is almost the size of the heat, this in fact slightly smaller in this particular example. Okay, so in this case, this is a Chennai 5-star hotel where 2,000 kVA DG sets were installed under this lower floor, and then the exhaust was piped out into the chimney. And before it was doing that, we put up some diverter dampers to route it through our heat exchanger as and when required. And the best part is the pressure drop in our heat exchanger was less than the back pressure that was offered by the conventional muffler. So there was no net back pressure on the engine when we diverted this exhaust gas through our heat exchanger as compared to the conventional muffler. Okay. Then these are modular systems, so you can have this photograph is for a 1250 kVA genset, and here you can see the deployment of sonic soot blower, okay, to dislodge any deposits that might occur periodically. And we also had a provision of manual soot blowing on this side. And this was, of course, for steam generation in this particular example. And we had multiple modules of these. Then we have also done gas turbine exhaust heat recovery system right up to 7.5 megawatt exhaust heat recovery. And our system was 1/3 the size of the conventional internationally accepted norm. Okay, we are heating thermic fluid from 230 degrees to 250 degrees in this case using the gas turbine exhaust. Then we had done Stentor exhaust heat recovery. We have done gas turbine, micro gas turbine, air-to-air heat recovery. And then we have also done exhaust heat recovery from dirty gases, but non-sticking exhaust gases, like in a coal-fired. Now this unit was deployed in the modern bakery plant in RML colony here, close to IIT Bombay. And in this particular case, we were doing the exhaust gases had lot of dry, fluffy soot, unburned carbon. So we had developed a heat exchanger where the heat exchanger's surface can be vibrated, and the entire dust would get collected down in this. So while earlier they had to recover heat, to open up the heat exchanger, conventional shell and tube heat exchanger, almost every day to clean up the tubes where soot would get deposited. After we installed this and we had automated the cleaning cycle as 20 seconds every 4 hours. And within 20 seconds of vibration, the entire dust which was deposited on the heat exchanger surface would drop down into the collection pan below, Okay, and the heat exchanger will be almost as clean as new. So we got a letter from the chief engineer after 3 months that they had not opened up the system for the last 3 months, and they wanted one more system like this. And then we gave them one more system, and then we licensed the technology to them to replicate it for the rest of their systems. So then we also have a variety of sorption refrigeration systems. Sorption is heat-operated refrigeration systems like vapor absorption, vapor adsorption, liquid desiccant systems, and so on and so forth. So we had developed hybrid air conditioning where liquid desiccants were used along with vapor compression systems for air conditioning application. Shipboard chilling using engine exhaust to produce chilled seawater for preserving fish without using any additional fuel. And now we have also developed something where we can generate potable water also as a byproduct of that same system. The liquid desiccant based solar multi-utility heat pump, which I think Professor Mehta might have talked about it during his presentation. So that was also one of the other systems. So here is a refrigerator, solar refrigerator cum water heater module, where the adsorption modules are covered with the evacuated glass tube, and the modules get heated up to, the adsorption modules get heated up to 180 to 200 degrees centigrade during the day when the sun is shining. And then the ammonia is regenerated, ammonia is condensed using the wire fin technology here. And then we collect the condensate ammonia, and then the condensed ammonia evaporates during the evening or night when the sun goes down and the modules cool down, or we circulate hot water in tap water in this and heat up the water by recovering heat from this. So this unit not only produces cooling effect, but also produces hot water from the same system. So the refrigerator cum water heater is based on this technology. And this adsorption technology can be as simple as this, where you have an activated carbon module here, or adsorbent module here with appropriate heat transfer enhancing mechanism put up inside the module. And then when you heat this module, the pressure goes up because of desorption, and then the pressurized refrigerant would condense on the other side if this is kept at ambient. And then after most of the ammonia has been driven out of this adsorption system, we would stop heating this and bring it back down to ambient using either air cooling or water cooling. And then when that is done, the pressure goes down, and at low pressure your ammonia evaporates, and as you can see the frosting on this particular thing here. Okay. So without moving any valves, just by switching on and off the heating and cooling circuits, you can produce cooling. Then this is a liquid desiccant based system where we are using, normally we want to maintain 27-60% RH in the room, let's say. So, but the dew point temperature of that air is close to 14 degrees or so. Now to maintain 14 degrees inside dew point inside the room, we have to cool the air down below that, and then you have to dehumidify that air. And so the evaporator of conventional air conditioning systems, the conventional DX system, is typically operating at 7.2 degrees centigrade. While in the case of chillers, the chilled evaporator might operate anywhere between 3 to 5 degrees centigrade, depending upon the chilled water temperature and so on and so forth. But in this case, by using liquid desiccants to do the dehumidification, you will see that we can increase the evaporator temperature to 12 degrees, 15 degrees, 18 degrees, or even up to 20 degrees, depending upon the application. And this increased evaporator temperature increases the evaporator pressure. Increased evaporator pressure leads to reduced pressure ratio. Reduced pressure ratio leads to improved COP and increased capacity also. So we'll see some of these advantages when we look at the detail. And the dilute liquid desiccant is then regenerated using the condenser heat. So the condenser heat is used to regenerate the dilute liquid desiccant, and that reduces the condensing temperature. Conventional air-cooled condenser with 35-degree ambient condition, which is the standard test condition, the typical condensing temperature is 54.4 degrees centigrade. But in our case, we could drop it down to almost 48 degrees centigrade also. So not only increasing the evaporator temperature, but reducing the condensing temperature concurrently helps improve the COP significantly, and up to 30 to 50% or even 60% improvement in COP is possible. So we'll see some of those things as we go along. Another technology which we have recently licensed and are introducing for various applications is this rotating contacting device. Okay, now this particular system is having closely packed disc on a rotor, and the water is irrigated off center to the rotating shaft, to the shaft of the rotor, and that loading of water in off-centric manner, if you can see closely here, the water which is pouring down here on this disc at an off-centered location enables this disc rotor to start rotating. And when the disc rotor starts rotating, it becomes wet uniformly, and then when air is sucked through we get the air to be humidified. So this can be used as a humidifier, it can be used as a dehumidifier. It has been already licensed as a wastewater vaporizer for industrial effluent treatment. And the beauty of this is we have handled very high TDS, right up to 2,70,000 TDS in industrial situations, and yet there is no scaling up of the disk, and there is no issues regarding corrosion and other things. And we have deployed these systems as evaporative condensers, as salt pan evaporation enhancers, and so on and so forth. And for this energy efficient vaporizer of waste water, our COPs in humid place like Mumbai was around 33 point. This was the photograph while it was being tested in our lab, just outside our lab. Okay, and in the plant in Barmer in Rajasthan, we had got COPs as high as 64.4. Now this is the ratio of the energy required to vaporize that water divided by the energy required to operate the pump and the fan. Okay, the fan power and the pump power is given here. Okay, so compared to that, the amount of water vaporized in Barmer was around 3,200 liters per day. So taking that ratio of the cooling, the heat required to vaporize this much of water divided by the energy that we have put in throughout the day gives us this particular COP. Of course, this system works well when the humidity, ambient humidity is low. Okay, the ambient humidity is very high, then this may not work. Okay, the main thing here is the very high surface area that we provide in a very compact space. Now, if you compare the surface area offered by all the discs provided here, which get wet, okay, as compared to the pool area is around 2.4 by 2.5 meters, less than about somewhere between 6 to 6.25 meters square. And the density and the surface area provided by the wet surface area provided by all the discs which are there on all four sides is around 1100 meters square. So the ratio of the pond area to this is almost 120. So if you're looking at solar ponds to vaporize wastewater or seawater, this can do significantly higher amount because of the 120 times increased 120 times increased surface area in this particular case. And the noise is also low. We have deployed these as cooling towers also. We'll see some of the slides later. Now, renewable energy based this, we have done plastic windmills. We had operated 2 windmills of 6 meter by 6 meter, 6 feet by 6 feet by 6 feet, and 8 feet by 8 feet by 8 feet for Mahindra and Mahindra. That was a later version of this. Okay. Then we have done solar plastic air heaters like these for Leh Ladakh area. Even in minus 20-degree ambient, we could go up to 40-45 degrees centigrade hot air being recovered in a single panel. No need of circulating the air through multiple panels. Okay, and then we have done steam generators. This was, I think, Professor Mehta might have shown you some of his this in case he has shared with you some of the photographs from his thesis. This is out of his thesis, Professor Mehta from MS University. And then these are air heaters which go up to 150 to 300 degrees centigrade in a single pass. So ambient air coming in and you can heat up the air right up to 300 degrees centigrade on a nice solar day. And these are non-tracking collectors. You can seasonally track them for optimal deployment. And then this was the refrigerator cum water heater which we developed for Godrej. This, and we have an ice bank also, stainless steel ice bank also inside. And what I showed you, the evacuate glass tube with the adsorption module inside, is all put up in here. Then recently, last few years, we have been developing flat plate type solar steam generators and flat plate type solar air heaters, which are very light in weight. The weight of the air heaters is as low as 7.5 kg per meter square. A conventional flat plate water heater might weigh anywhere between 25 to 35 kg per meter square, while this, as you can see, is very light. And in spite of that, the efficiency is much better in this particular case. On a good sunny day, we easily reach efficiencies as high as 80% based on the global radiation. And for steam generation also, typical efficiency is between 40 to 60%, depending upon if it is a nice solar day with good sunshine, then we might go up to 60% efficiency also based on the global radiation. Most of the tracking type solar collectors, on the other hand, will find it very difficult to get 60% efficiency based on global radiation. They give 70% based on 70% based on beam radiation. But at times, if you normalize it for the global radiation, which they don't, they are not capable of collecting entire this because they are concentrating type. Okay, in that case, our heat delivered per meter square is higher in our case than compared to that. These are some of the earlier prices for the air heaters, and this is 5,000 to 9,000 rupees per meter square. If they are mass produced, the numbers can come down significantly as low as 6,000 rupees also. And then for steam generators without storage, the values are between 6 to 7,500 when mass produced, and in smaller quantities they can be going up to 10,000 rupees. And they can be used for cooking, process heating, residential, commercial, and industrial establishment. We have deployed 27 collectors of 2.1 meters square each as a roof of a facility in Nagaland for a agro-produce drying facility. You'll see some of those slides also coming up later. Then further, we have also developed solar steam generators for indoor cooking. And cooking inherently is not a continuous process. It is intermittent. So you need to generate and store the cooling effect as and when it is available, and then continue using it throughout the day as and when it is required. So we had integrated storage within the collector itself. So that helps us eliminate any cooling loop, heat transfer fluids, and any pumps associated or heat pipes associated for that and things like that. And we are able to extend the useful heat delivery period by about 2 to 3 hours beyond sunset also. So even 2 hours after sunset, we could still produce cook indoor. And we have produced idli even on a full moon night at around 7 o'clock when at around 7:30 when the sun had already set 2 hours before that time. Okay. And we could cook idli just in 15 minutes, just like what you do in indoor on your gas stove or others. Okay, and in this case, the storage media temperature goes all the way up to 245 degrees centigrade. And the efficiency also is 40 to 60% on a good solar day. That global radiation-based efficiency is as high as 60%. And the cost increases because of the storage compared to the earlier one. But in mass-produced case, it can be as low as 1,000 rupees per meter square, and this I believe is much lower than most of the collectors that you can have. And the simplicity of the installation. You just have the overhead tank connection to this, and then you can have the steam connection going into your kitchen. Okay, here you can see that the rice cooker for 75 kg was set up just below the collector here. This. Okay. Then we have solar air heaters, which are deployed for space air heating. Okay, and we had integrated storage along with that, so that at night time also the same system can generate this. And 1 meter square solar collector can draw air from 20 meter square of the solar 1 meter square solar PV can power the fan to draw air from 20 meters square of this solar aerator. And this is possible because of the extremely low pressure drop across our solar aerator. Typically varying between 1.6 to 5 mm of water column only. Okay. And in a single pass, this typical collector is 2.1 meter square, 2.1 meter long, and the width is 1 meter. In this particular case, the air comes in from this end as well as that end, and then by the time it goes to the center where it is extracted out from the backside, you get hot air at the required temperature. So in this case, we have the maximum temperature that we have achieved in this particular type of, this is as high as 119.6 degrees centigrade in Mumbai. Okay. This is non-tracking collector, but the efficiency drops off to almost 37% there. So typically, if we are using this for air heating at about 75 degrees, we can expect 80% easily. Then we have used heat pumps for cold store operation, and to improve the economic sustainability of the cold store, we are recovering the condenser heat and using it for drying of agro produce. So this is the drying side of the agro. This we would put the trays here and cover this up, and then the condenser air will help us dry the produce in this case. And the indoor was maintained at 6 degrees centigrade here. And this was set up in Nagaland, and we had ice bank tanks deployed as the evaporator of this. So even if the electricity is not available for up to 4 hours, you'll continue to get the cooling effect without much difficulty. So here at the same facility, we had, as I said, 27 collectors of 2.1 meters square each were deployed as a roof. And then they were ducted together, and this in 3 rows. This is 9 collectors here, another 9 collectors, and the other 9 collectors in a separate thing. And then the hot air from these were sucked in, and there were 2 fans here, and the fans would suck in the warm air and then pass it over the drying. This was a agro-produce dryer, and the material was kept inside trays here, and the warm air would pass through this and then dry the thing. And this was a biomass backed up dryer. So during night, if they wanted to continue the drying process, it was urgent to dry it, they could fire wood and biomass and continue the drying process. Or if it is raining outside and you don't have enough hot air, or you don't have any hot air, then the biomass fired dryer could operate also. Here also, as you can say, for 27 collectors of 2.1 meters square each. Okay, we had only 3 meters square of PV panel, okay, to draw out air from that. And these 3 PV panel were supplying power to the fan here, which was there. It was the axial fan, low pressure drop fan, pressure head fan, and that was this. And these are some of the products that were dried using that. Okay, this is a dried large cardamom. This is Naga chili, which is a very, very hot and chili, and has very high value in the market. It is exported also. This, and then this is some bamboo shoots, and then ginger and some ginger candy. So these were some of the products that dried in the heat pump assisted dryer as well as the solar dryer. Some of the economics of those dryers are shown here. So cold store rating of 2.5 tons. Okay, the moisture removal rate in this particular case was 100 kgs per day, and initial investment, including the dryer and the cold store and everything. The cold store was this much, and the conventional cold store and air conditioning system would be this. So the difference between our system, which had a multi-utility heat pump and a dryer, and this was 5 lakh rupees. So when we looked at the payback period for this, based on this additional cost that we have to pay for this, the payback came out to be just 187 days for ginger, where the ginger was assumed to be costing 110 rupees per kg at the peak harvesting season, and the your selling price, this was there also, that was accounted for and all. And in this case, during the peak this season, the Naga chilies would cost somewhere around 100 rupees per kg, the wet form. Okay. So the value added product would be sold at almost 2000 rupees per kg, and we took 50% of that value as the actual price, and that the farmer can realize, keeping 50% margin for all the other marketing and other intermediary persons. And even with that, the payback period was achieved to be just 65 days for Naga chili, for the our cold store cum dryer. And for the solar dryer itself, the cold store cum dryer, which was electrically operated. And for the solar dryer with biomass backup, the Naga chili had a payback of 77 days. Now, 77 days for a solar project is an extremely attractive payback period. The ginger payback period was around 225 days, so that's still less than one actual year. Okay. So if you look at what is the, this was a project sponsored by DST, Value Addition of Agro-Produce. So we use multi-utility heat pumps to operate a cold store and simultaneously do the drying. Okay. So the cold store operation is improved because of heat recovery. Okay. And the drying was, of course, free, and we could do low temperature drying because the heat available was almost free. So we are not too worried about drying efficiency and other things. And we could liberally circulate this. So because the drying occurred at low temperature, the aroma retention was very good, the color retention was very good, and we were able to get good benefits out of the produce. So solar air heating with PV powered this, so we can have 100% auxiliary power saving is there in this, because the power is generated using the PV itself, and this can be deployed in an off-grid location also in this case. And then biomass was used as backup for the solar power, this in case it needed to be operated. Now coming to the tube heat exchanger, I have another 15-20 minutes. How much time do I have, Professor? Hello.
Yes, sir. 20 minutes.
20 minutes. Okay, so I will now rush through the thing. I've given you the introduction. The presentation will be available to you, so you can go through it later. Okay. So this is the tube heat exchanger. We had talked about the 2-tube configuration. Then you can have 3-tube configuration. And you can have more tubes also in this particular case. Now, in this case, as I said, the main features of these are modular in nature, so there are no lower or upper limit in capacity. We have done a small heat exchanger of 0.5 ton capacity also, and we have done up to 270 ton capacity also. And if somebody asks us to do a 3000 also, we will not hesitate in designing, deploying them. And this, they're vented double walls, so they're essentially safe against mixing of fluids. The high transfer coefficients are ensured because of this unique bends and this straight lines intertwined between them. The material of construction, you can have different tubes, tube materials for the different sides. So mixing and matching is possible. So you don't have to go to very fancy materials of construction which are compatible with both the fluids. Just to give you an example, if you have ammonia and seawater, the only common material which is readily available is titanium, but then titanium heat exchangers can be very costly and difficult to manufacture. While in our case, we used stainless steel on the ammonia side or carbon steel on the ammonia side, and we used cupronickel on the seawater side. So the cost of the heat exchanger can be much lower than the traditional alternatives, without compromising the compactness or safety or inventory this of the heat exchangers. Then easy to maintain because you're just cleaning in place. You just circulate the cleaning fluid if there is any scaling or thing like that. It is simple to fabricate in this once you have the design programs. So we have deployed these for heat recovery from radiator hot water, superheat recovery from condensers, from various residential, commercial, industrial applications. Liquid desiccant can be regenerated using this, as I said, in a hybrid air conditioning system. Fuel oil heating, thermic fluid heating, water heating, even flame-proof electric oil heaters and transfer oil cooling, heating and cooling of potable water, heating and cooling of temperature-sensitive fluids like honey, milk, fruit juices. This we can have fruit juices also being heated with fibrous material and trained it without any difficulty. In fact, in the Mahindra and Mahindra application, there are fine metallic grit inside the thing in spite of filtration, and most of the other heat exchangers would choke up. Plate heat exchangers would not work. Shelling tubes will get deposited and choked in time. Tube in tube and other things are not reliable either because of similar reasons. But our systems could work very effectively in those cases also. We can use these as tubular reactors also for chlorination, bromination, sulfonation and other reactions. So superheat recovery, basically after the compressor, the vapors are quite hot and we can recover. Like in ammonia case, the vapor could be anywhere between 100 to 115 degrees centigrade, or at times, sometimes even higher. So it's we had recovered hot water right up to 84 degrees centigrade in an ammonia dairy installation at Worli. So superheat recovery can again find applications in residential, commercial, industrial applications, and they can be used for many different applications as we have just discussed. They not only reduce the power consumption of the refrigeration chilling equipment, the fuel required for the hot utility generation is of course 100% eliminated. And in fact, their initial cost can be lower than the cost of a comparable capacity oil-fired system or gas-fired system. Okay, low maintenance charge and payback periods we realize are 3 to 12 months. These are some examples of some installations in NDRI dairy by one of my licensees where the payback period was less than 6 months. Water heated from 30 to 60. Refrigerant was being condensed, cooled from 100 to 50 degrees centigrade on a 60-ton chiller. So this unit got integrated in less than half a day. Okay, so no significant downtime is required for that. And the heat exchanger on the ammonia side was carbon steel and stainless steel on the water side. This was at the Hotel Fariaz, as I told you. My PhD student, Professor Tandle, who worked in that this at that time, he had helped in fabrication of this, got it fabricated. Okay, and in this case, we are generating hot water up to 24,000 liters per day, heating water from 30 to 60 degrees. The 9-year-old chiller, the COP, the chiller power consumption went down by 20%. Okay, and the chiller capacity went up by 30%. Okay, actually, the power consumption, this is actually not power consumption. Power consumption went up by 10%. COP went up by 20%. Okay, so the COP went up by 20% because power consumption increased by 10%, but the cooling capacity increased by 30%. Okay, and the payback, we had told them 6-month payback, but they actually got 2.86 months payback, and there is saving about 1,100 tons of CO2 emission in the 11 years that they operated it. And the best part is when they scrapped the heat exchanger after 11 years because the chiller life was 20 years had passed. Okay, they got 5 lakh rupees as scrap value for the heat exchanger, while the actual heat exchanger installed was for 2 lakh rupees when it was initially deployed by my client. Okay, and of course the annual saving was as high as 10 lakh rupees per year because of the fuel cost going up. Daily fuel saving was around 81 liters of diesel. At Worli Dairy, we did another project where 70,000 liters of hot water was generated. Both the ammonia and the water side were made out of stainless steel tubes of 1/4 inch diameter. Okay, and the chiller power consumption went down by 5%, and the hot water recovery was of course free. 140 horsepower pump on the condenser water cooling side could be shut off because of that. And of course, they saved water in the cooling tower because this much of heat was recovered here. So again, here the payback period promised was less than 6 months, and they actually got it less than 6 months. Saving was 23 lakhs per year, while the install cost was only 10 lakh at that time. Okay, this also operated for more than I think 8 to 9 years without any difficulty. Then these were the superheat recovery water heater for McDonald, where 240 liters of water was this. Okay, and the power consumption reduced by 12 to 15.6% compared to the one without having the desuperheater. Okay, in this case, the desuperheater was packed on within the condensing unit itself. These were the older condensing units where we had enough room inside. Nowadays, the condensing units are also so compact that we typically have to put it outside. Okay, so various types of heat pumps. You can have heating only heat pump, heating in winter and cooling and dehumidification in summer and monsoon, the reversible heat pump, which we have in market, and simultaneous heating and cooling is what we offer, and multi-utility heat pumps are what we offer. And the best part is the utilities can be generated and tapped as and when required, and there is no compulsion that you should have air conditioner running when the hot water is required, and so on and so forth. Also, these heat pumps can be of absorption or adsorption type. They can be co-generating or tri-generation of cold, hot, and dehumidification utilities. So like you can have a solar refrigerator come water heater, solar dehumidified fresh air, portable water generation, and water heating, like what Professor Mehta might have talked about his thesis at IIT Bombay. Then solar cold store come dryer, solar biogas fired cold store come dryer, and solar cold store come dryer with biomass backup, so that in case sun is not available, you can continue with biogas. And let me tell you that we foresee that in future biogas availability of biogas is going to increase because of the increased cattle and processing of the cattle dung and other things. And we expect that these things will again come back into the mainstream, the absorption, adsorption systems. Of course, we need to keep the COPs as high as we can get so that it is worth using that biogas for that application. And then, of course, tractor cabin air conditioning using engine exhaust, shipboard cooling using engine exhaust, and so on and so forth. This was the first Mahindra and Mahindra unit that we built, giving about 66% energy saving, 33 kilowatt heating duty with only 11 kilowatt input power. Earlier, they were using 33 kilowatt of electric heaters to do this. And while they are saving 66% energy, we are giving them portable chilled water and air conditioning of the shop floor as bonus utilities. These were some of my students. Professor Sadiq was the person who worked on the shipboard chilling unit. The Ethiopian student here worked on the refrigerator, solar refrigerator come water heater, and so on and so forth. Okay. So in the first unit, we had with heating cleaning solution from 50 to 55 degrees for generating potable water and air conditioning, all three from the same unit. So as I said, this was the unit, and we also, this was a, then say after the first unit was deployed, they were happy with the performance. They said, can you reduce the footprint? So we reduced the footprint to just 1 meter by 1 meter in this particular case. And then this was with a 8.3 ton compressor. And then we also were able to deploy a 12 ton compressor in the same footprint with the evaporator stretching up all the way to the top on both sides. Okay. And so this was 36 kilowatt, that was around 55 kilowatt. Okay. So using, this was with 12 kilowatt input, we are giving 36 kilowatt of heating, and we are simultaneously giving up to 24 kilowatt of air conditioning. And if part of the air conditioning is tapped out as chilled water, then you get reduced air conditioning. Then we also had a water-to-water heat pump for textile application, where water was heated from 27 degrees to 60 degrees centigrade. 55 kilowatt of hot water was produced with only 15 kilowatt of input electricity, and 43 kilowatt of chilled water was co-produced with that. So this can be used for air conditioning, and this can be used for as a hot utility. So overall COP, if you look at it, it is very high. Okay, more than this. So this was, I have already described to you this unit. Here the power input was only 1.01 kilowatt electric per ton of this. And comparable system at that time, the power consumption of our system was 25 to 36% less than the air-cooled unit which we replaced there, which was, I think, from Blue Star or Voltas. Then this I have described to you in detail. These are the calculations. So although this is only a 12-ton heat pump, the instantaneous heating duty can be as high as 35 kilowatt of water heating per this, and 62 kilowatt of potable hot water for cooking. So at 90 degrees centigrade, if you 95 degree centigrade, if you get hot water, you just put rice in it and it will cook itself without heating. For vegetable and dal, of course, you need to continue to heat it and process it. So it was generating hot water for utility, cleaning of utensils and various other floor and other things. It was generating potable water for cooking. It was generating chilled water for drinking, and it was also maintaining a refrigerator cool. Then recently we have licensed the technology for multi-utility heat pump for instant milk chilling. Okay, this has built-in thermal storage, and this is a Ahmedabad-based company only, where you pour the milk and instantly it gets cooled. Within 1 hour, you can cool 250 liters in the morning and 250 liters in the evening in this particular model here. Okay, and it also produces hot water for sanitation as a byproduct. So compared to the conventional bulk milk coolers, which consume for 500 liter per day capacity, the peak power is around 2.7 kilowatt. Our peak power is about 1 kilowatt. Okay. The energy saving is also there because we are generating potable, means sanitary water is heated up to 55 degrees centigrade. So that gives additional saving of 3.5 kilowatt hours per day. Okay. And conventional bulk milk cooler cool the milk within 3 hours. Ours is able to cool it in less than 1 hour if the entire 250 liter is poured together. But if you take the time from when the milk is poured to the time it takes for the milk to travel through the heat exchanger, it's only 30 seconds, less than 30 seconds actually. These are some panel heat exchangers, this which we have deployed for air conditioning. In fact, the panel which you see behind me here in my bedroom, that has been installed here for more than 6 years, and without any servicing, it has been performing quite well. Every day, this is integrated with the heat pump which I have. So these are some examples of the panel heat exchangers. This is another panel installed in my dining area. This is a different type of panel. And we are able to dispense about 1.8 in 1.8 meters square frontal area. We are able to dispense 1 ton. Typically, the conventional panel radiant heat exchangers require about 20 to 40 meters square per ton because they don't handle condensation. They can't handle condensation. You need precise control of temperature and humidity also and things like that. But in our case, we don't have this, and this is a DX system. The multi-utility heat pump, 4-in-1 multi-utility heat pump, which has been operating in my house for the last 15 plus years. In fact, 17 years now. Okay. About 6-7 years ago, we replaced these with these panels because the indoor unit after 10 years started making noise, the conventional indoor unit. So now we have replaced this with a fanless unit, and we use the ceiling fan to improve the performance. This is the similar unit inside my office area, the radiant condenser for a water cooler. Then I showed you the radiant evaporator in the Nagaland project. Then we have rotating contacting device. We have some biogas scrubbers using this rotating contacting device. Okay, so flotation device here, air-to-air heat recovery using liquid desiccants. So again, the rotating contacting device, it's a simple system, modular in nature, very versatile because you can have very large. Hello. Yeah. So you can have a very wide range of L by G ratio, that is the liquid to gas ratios. Okay. And no limit in capacity, very low carryover, high mass transfer coefficients because of the rotation and renewal of the surface on the disk as well as the liquid disk. And then of course you have very low pressure drop because air passes parallel to the disk. Maintenance is not an issue. We can give you the disk in the material that is required for that particular process, and cleaning using a jet is sufficient. So we have deployed the possible applications for this rotating contacting device is aeration for water bodies, ponds, lake, fish farms, BOD, COD control, air conditioning applications like humidifiers, liquid desiccant dehumidifiers, air washers, air-to-air heat recovery, cooling towers, evaporative coolers, indirect evaporative coolers, seawater-based cooling towers and indirect evaporative coolers, liquid desiccant-based regeneration in this. Okay, scrubbing of gases, biogas purification to remove H2S and CO2, exhaust gas scrubbing for kitchen exhaust, laboratory hood, this industrial furnaces, and then you're also likely to do a crematorium furnace exhaust heat recovery scrubbing. Waste heat water vaporization and effluent concentration for RO plants. This has already been licensed. Okay. Then dairies, pharmaceuticals, and all. So these are some of the applications, and we have already gone through this particular slide earlier. There is the cooling tower, a 200-ton cooling tower which we had built, integrated, and deployed. Okay. And conventional cooling tower had a power consumption of 7.5 kilowatt for the fan. Ours was now at that time first unit was 1.66. Now we have reduced this down to 1.5 kilowatt. Okay. Then this is mainly because of the low pressure drop across this. So all 6 sides of the hexagon are active mass transfer units in this case. Okay. Then we have wire fin heat exchangers where we have 3 European patents also, and we're deploying these for various applications now. I think I'll skip some of these things. I'll just go to the applications. Air conditioning for condensers, evaporators, desuperrators. In fact, we are integrating the air source heat pump for the European market right now in the lab with this technology. And it is expected to be sent for certification in Europe. And we expect that it will be better than the best worldwide, giving better performance than some of the companies like Daikin and Mitsubishi, who are currently catering to that market there in Europe, with much better features than what they are offering at this point. These can also be used for dry coolers for fuel cell vehicles, radiators, transformer oil cooling, lube oil cooling, power plant condensers, and this for solar power plants and others. Then compressed air coolers, then cooling water for high performance data centers. We are also having a project going on that. Then indirect evaporative coolers using seawater. This we are doing for shipboard chilling, for engine room cooling for Navy. We have submitted one project which is likely to come through. So various applications we can have. And we are also use these as ice bank in ice bank tanks and phase change material storage media for improving conductance. Diabetic contacting device, this was what was used in the McDonald unit. Okay. So some of the applications, efficient absorption and separation of this, distillation, rectification, solvent heat recovery, hybrid air conditioning, liquid desiccant based dehumidifiers in this. So these are some of the prototypes. You can see this was how the schematic for the McDonald unit. This was the McDonald unit. This is a schematic for the McDonald unit. So you have the indoor unit being supplied with the liquid refrigerant, and then the refrigerant which we have integrated water chiller, then the compressor, superheat recovery, and the excess heat is going into the evaporative condensation board. And we have hybrid air conditioning where we can go from 1 to 4 in a single step. So the refrigerant circuit and the liquid desiccant circuit are integrated using our diabetic contacting device. So the cooled liquid desiccant is dehumidifying and cooling the air in a single step, right from here to here, instead of going all the way like this. You can go from here to here, and you can see that the minimum temperature is much higher, so our evaporator can be much higher. Here the minimum temperature was here, so our evaporator was typically 7.2 degrees here. Okay, so increasing the evaporator temperature increases the cooling capacity because evaporative pressure goes up, density of vapor goes up. So the mass flow rate through the compressor goes up. Energy saving is high, modular design, low initial cost. So COP higher than 5 is also possible with this. Now this was done by one of my PhD students, Dr. Roshni Iso, who is also active nowadays. She was the past president of ISRE. This also. Now we have this that will be going up to even 5 COP and without any moving parts in that. So then we have air-to-air heat recovery units. I think I'll stop here. We have gone through some of these. These are some of the installations. Then the exhaust heat recovery units I have already described. These are the air heaters, as I said. In this air heater, we could heat up the air up to 119.6 degrees centigrade from around 33 degrees centigrade. Okay, this particular this data is for 104 degrees, 33 to 104 in one. So the 33 degree air enters here and the 104 degree air comes out from here. Just in less than 2 feet travel, we are able to heat it up. And the weight is also very less. These are the air heaters for high temperature. You can see throughout the day, right from the morning, the temperatures are around 150 degrees, peaking up to around 288 in this particular case. And then even in the evening, it's more than 150 degrees at 5:30 in the evening. And the daytime 9-hour efficiency is more than 61.8%. The year-round performance, and we see that the east-west performance orientation is better compared to the north-south. Okay. You must have seen Professor Mehta's slides on these. This is the steam generation using the solar steam generator. Throughout the day, you can generate steam without any interruption. So our papers, many of these technologies are described in ISRE journal. This is what you might have seen, Professor Mehta's work from MSU, Baroda. By the way, Professor, these type of collectors, Professor Bhatt did the preliminary work, and this later on the work was extended by Professor PM Meena. This is Professor PM Meena's work, but before this, Professor Mehta had done work where we had gone up to, I think, 180 degrees centigrade, if I'm not mistaken. And then he took it up to 320 degrees. Okay. And we had a solar cooking system for 300 people with 75 kg rice. This earlier, by the way, that earlier box which I showed you was for 25 kg rice. Okay, this is for 75 kg rice. Cooked in less than 60 minutes. Good enough for 300 people. And this can be cooked twice a day using storage type collectors. Liquid desiccant. Now some of the technologies that we have deployed is matrix heat recovery exchangers, tube-tube heat exchangers for various applications, multi-utility heat pump, contacting devices for various applications, absorption modules, plastic heat exchangers, panel heat and mass exchangers, plastic windmills, solar collector with integrated absorbers, solar air heaters with storage, rotating heat and mass transfer units. So in conclusions, we can say plastic and aluminum air-to-air heat recovery units can be used for air conditioning systems. Attractive paybacks can be realized while improving the indoor quality using dedicated outdoor air systems. Exhaust heat recovery systems from engines and gas turbines, furnaces, tenters can give you payback of 6 to 18 months, depending upon this using our matrix heat recovery unit. Efficient commercially available absorption systems, typically double effect LIBR system, COP might be between 1.2 to 1.5. Single effect ammonia water gives you COP between 0.3 to 0.66, 0.3 for minus 20, minus 30, minus 50 degrees centigrade evaporator temperatures. Then your liquid desiccant based triple multi-utility heat pump for fresh water fresh air dehumidification, potable water generation, and water heating applications. We have gone COPs up to, Professor Mehta had taken this up to, I think, he had actually registered a COP of 1.03 in a physical system, and it predicted COPs up to 1.6. Now we have COPs, predicted COPs from 1.6 to 2 also with these systems now. And we have multiple utilities being generated through the same system: fresh water dehumidification, potable water chilling in this. There's an Ethiopian student, Tarike, who had worked after Professor Mehta's finished his thesis. And we have eliminated a lot of rotating contacting media into a stationary contacting media using column film heat exchangers, and improved liquid desiccant regeneration system, right up to 90% effectiveness of solution heat exchanger. And that is what has helped us move the COPs up. So superheat recovery water heaters and heat pumps can address our concern for increasing environmental concerns, okay, by recovering free hot water and reducing the emissions. The patented tube-tube heat exchanger eliminates the worries of cross-contamination. Payback periods can be 3 to 6 months for superheat recovery and 3 to 18 months for multi-utility heat pumps, depending upon the duration of their usage and all. And then affordable solar collectors are available now. So for air heating, once through air heating up to 75 degrees, once through air heating up to 300 degrees for various applications like solar milk dryers, solar ovens, solar indoor cooking, and solar fresh air dehumidifiers, and so on and so forth. And then steam generators can be used for indoor cooking, for milk pasteurization, solar cooking, drying, space heating, and process heating applications. And multi-utility generators can be used for air conditioning, drying, potable water generation. Okay, and so opening up new possibilities for sustainable development based on energy efficient technologies. These are some of the technologies which we are licensed for various things. And thank you very much for your patient hearing. I can take a few questions if there are any. Thank you. I'm done.
Participants, you can ask questions if you have.
So all the participants, as we have followed during all the session, if you will not receive any question in next 30 seconds, we will close the session.
So assuming no questions from the participants, on behalf of entire team and participants, I'm very much thankful to Rane sir. Sir, thank you very much for fruitful and informative session. Thank you very much, sir.
Thank you very much. Namaskar,
Thank you,
and
sir.
all the best for your program.
Yes, sir. Thank you very much. Thank you,
Okay.
sir.
Thank you. Thank you, Professor.
Okay. Thank you, sir.